Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, today we're in the lab with EPC. They're just blowing my mind. Well, they're actually proving me right. You know, I've been saying GaN is the future, right? Well, I've been saying also the future is here, and it is. I showed this little 16th brick module, like 300 watts capable. That is just nuts. Sits on this little motherboard, so fixture here where you can test it. Well, now they've sent me an 8th brick, so it's bigger. It's that module right here. I'll bring the camera over, show you a close-up of this. Yeah, I'm going to show you some cool stuff right here. But what I want to do is I want to just say that this guy right here is nuts. 1,000 watts in that package. It's an LLC controller, no less. So, pretty complicated controller. A little module, heatsink on both sides, 1,000 watts. Let's take a look at some documentation just so you can see from EPC what they've done here, okay? Alright, so here's the data sheet for this module. Now you can see a nice clear picture of those FETs. The 4 FETs across here and the 2 FETs up here. They're not blue in this picture, but you can see them up here. And then if you just look down here, and you can see a lot of the capacitors here, right? But if you look down here, you can kind of see the same schematic, you know, the 4 transistors in the bridge configuration on the left, and then the resonant components, the CR, the LR, and the transformer. And in this case it's showing like a single transformer with your dual outputs here, and you have all your transistors, your synchronous FETs. You got a block diagram showing the housekeeping power supply, that 3.3 and 5 volt supply running your controller, your gate drives, and then you have your power stage. And there's your specs for this. Input voltage 36 to 60, outputs 12. 2 important things: you can run it at 0, you don't have to have a minimum load, and then you can also run it at 83 amps. So down here's your heatsink requirements. Okay, what I want to do is I want to show you what they've done and how they've assembled this to see how they could get that much power into this small package. First of all, it starts with the eGaN FETs. I mean, this thing has 12 FETs. Yes, 12 well, they're not MOSFETs. I was going to say MOSFET. eGaN FETs, enhancement mode GaN FETs. 12 of them in that package. Well, you don't see a transformer. There's isolation here too. So that isolation is provided by planar magnetics. What that is when you put a PCB board instead of windings, so that you can use, you know, essentially it's like flat wire, but you put the patterns in the PCB board. Well, often there'll be a PCB board in a magnetic, you know, between the ferrite that sits on top of another board. Well, when you start getting things switching fast and you take the time to lay out the board properly and you want things really short and tight, then you integrate the magnetic into the actual board that all the circuitry's on, and that's what they've done here. So let's just go take a look at that, because it's pretty impressive. I mean, even if you imagine that stuff being 4 times bigger than what it is, it's impressive. But in this package, yeah, crazy. Let's go take a look to see how they put this thing together. I want to just show you the board. You can see the 2 sides of the board, the magnetics, right? So this is an integrated transformer. The board is integrated into the transformer, so that's really cool. And that way you don't have leads. You're just using the traces on the board. Very efficient. You can see the capacitors on top and bottom of the board here on the right side. So there's the dimensions, very small. Okay, there's the motherboard. This is where our 1/8 brick module gets plugged into. But here's the volt capacitors on the output, the volt capacitors on the input. And there's a picture showing the module installed. Okay, there's a cool picture showing the thermal of the board when it's running. Now, this is where I want to show you the thermal management of this. You've got this heat sink arrangement. Everything gets sandwiched down to keep this thing running cool. Let's take a look at it. Pretty cool, right? So there's the two different views right there. Now let's look how that's actually done. So this is pretty neat. They put a little bit of gap filler right here in this corner because you got the two FETs here, you got the other FETs down here, and you're going to put a heat sink. So you've got this little copper spacer right here, right? And then you got these pads put on your transistors. See the pads up here covering those two, and the ones covering the big ones down here. So now put a little bit more gap filler, and then you put these heat spreaders. Now you really have an even surface with your magnetic. You actually have to put a pad on the magnetic. One thing that's going to protect the magnetic from having metal directly on it. The other thing is going to help pull the heat out of it and give a little cushion, you know, for the ferrite and the metal. So then you take your heat sink and you put a pad on that. You can see there's 3 holes in it. Right here, 3 mounting holes. Okay, then the other side of the board, you have your other 2 FETs right here and your other 4 FETs for your other output. And you put some more gap filler, do the same kind of construction, the copper spacer, the thermal pads. Then you put a little bit more filler on top of that copper pad. Then you have your heat spreaders again. Now you got your thermal pad on your ferrite. Then you put another thermal pad on your heat sink. And look at that. You got a sandwich. That's pretty impressive, right? Well, now the only way they can do that is to switch very fast so that you don't need a lot of turns in your transformer. So if you switch fast enough, you can use fewer turns and still transfer that energy from primary to secondary side. So they're switching this thing at 1 megahertz. I mean, for that kind of power levels, that's just, boy, that's crazy. So that's how they did it. Okay, I mean, it's really impressive. I keep saying I just can't get over it. But anyway, okay, so what I want to do is, well, first of all, I want to tell you that what they've accomplished is 1,200, well, over 1,200 watts. I think it's 1,227 watts per cubic inch. I mean, I was impressed with this guy. 300 watts in right around a cubic inch. That, to me, that's super impressive. Now we have isolation, and yeah, I guess I just keep saying it. It's just blowing my mind. Okay, let's just go look at some performance curves so you can see kind of what I'm talking about, okay? For performance, this is pretty darn nice. Look on the left, you got the voltage on the output. You know, 12.05 volts at the top, 11.6 at the bottom. In the blue, you can see that it starts off at 12 volts, and as you increase the current, you go up to 83 amps and you drop down to what? Just above 11.65. So you lose just a little bit of voltage with all that current. That's just crazy, 83 amps. Now that's with an input voltage. See the red? That's holding the input voltage solid at 48 volts. Now here's the soft start circuit, how it works. As the input voltage jumps up, there's a controller inhibit time. It's going to force a time before it lets it start to operate. And then once it comes up, the output pops up. Looks like a slight overshoot, and then the output. So that's at 10 milliseconds per division. If you zoom into that 1 millisecond per division, just look at the rise time, you can kind of see what it looks like as it comes up. And you know, that's pretty darn cool, right? Now this is an important graph here. This is pretty cool. The efficiency. You notice right up to here, say 400 watts, you're about just above 9 watts loss. And these last few watts, just before 400 watts, it starts to this curve starts to, it kind of ramps up, right? But right through here, say 300 to 400, you're down where that's not a lot of watts in that package. That's not too bad. So, but then between, say, halfway, the watts right in here, what is that, like say 12 watts? Between that and full output power, you're going to go up to close to 34 watts. So you can see how the curve just kind of takes off. And also the efficiency is dropping a little bit. So really right around 400 watts, you have a pretty darn good operating point because efficiency's very high. It's above 97%. Your power drop in this range is right around 9 watts. That's not hard to get rid of in that package. So, really, geez, that's a pretty nice small brick to get 400 watts out of without having to go to great lengths for thermal packaging. All right, so you can see how small those FETs were on the board. I mean, well, scale-wise, relative, everything's relative, but they're really small FETs. I mean, like say 12 of them in here. Let's take a look at what they look like, okay? Let's look at those specs to see how 12 FETs can put out this kind of power. Okay, this is a synchronous rectifier. This is the eGaN FET, and you can see 40 volt rated, 1.5 milliohms, 90 amps for current on the drain, and pulse current 560 amps capability. And this is crazy. Now look at this dimension here, 6 millimeters by 2.3 millimeter. And that is pretty small. Looks big on the board just because everything is relative, but that is a pretty small die, and it's actually kind of a crazy looking package, right? All right, now here what we have is the eGaN for the bridge, and it is the 100 volt 3.2 milliohm, 60 amps for drain current. Pulse current can go as high as 231 amps. So good for Class D. See the applications over here. I mean, this guy is just crazy. 3.5 millimeter by 1.95. This is an awesome FET. I mean, the 100 volt range on this gives just a lot of different applications you can use it in. All right, so you know what? I think we ought to go look at the schematic, and we'll just take a quick look. It's pretty complicated and all that. There's a lot of stuff going on, but it's kind of broken down into certain pages, which when you look at it that way, I guess overall the schematic's not that complicated. The complexity comes in the microchip. Let's go look at the schematic. All right, here what we have is the power stage. You can see the 4 transistors here in the bridge configuration, right? So you would have alternating FETs turned on. You'd have these 2 GaN FETs turned on, and then they would turn off, and then these 2 guys would turn on. So when say this FET up in the left corner and bottom right corner turned on, then you have conduction path through. Now these are transformers. They just simplify the drawing. So you go through this primary, through the resonant capacitor, through this primary, and then back through the bottom FET. And then when they turn off, you go through the other 2 FETs, and the current would go the opposite direction to the transformers. So you're essentially push-pulling these transformers up and down. Now these transformers, obviously the input side, they're in series, right? The output is actually in parallel. You see the center tap right here comes out here to V out, and this is V out as well. So they're just in parallel. You could use one transformer with parallel FETs, but this arrangement works better where the secondary, the transformer, is actually driving each set of FETs. That way they parallel better. Let's look up here. Here's all the input capacitors, all these capacitors in parallel, okay? Bunch of 1 microfarads, and a bunch of 220 nanofarads. So you got the high frequency HF, high frequency caps, and then you have all the other ceramics, which are, high frequency as well. And then look at all these caps right here, 22 microfarads for the V out. Just lots of them in parallel. Just a ton. Alright guys, let's go down and look at this other page, okay? This other page has a bunch more capacitors. These are over here on the left. These are all input capacitors. Some are ceramics, some are larger bulk capacitors, these 47 microfarad caps. And then over here we have a bunch of output capacitors, a bunch more 22 microfarad caps, and they look like they're ceramics. And then to the far right we have the 390 microfarad bulk capacitors. So lots of capacitors on this thing. And then down here we have this little board. It shows the GP connections, transmit. Here, let me just show you that schematic. So you're coming in here with this USB, comes in through a common mode choke here, and there's your chip right there for your USB, and here's your output, transmit and receive, and there's your driver chip, your isolation. That's a nice circuit there too for USB. Provides isolated output. Okay, now what I want to show you is the drivers for all those FETs. They're on this page here. You see on the left here we have the ones for the input stage, the bridge, and the ones over here on the right, these drivers are for those synchronous rectifiers, the synchronous FETs on the output. So you got a high side and a low side driver on each output stage. Okay, and here's the brains of the operation. This is the PIC by Microchip. You can see it's a lot of pins. The driver stages are over here. They're driving those drive chips that we just looked at. And here's the input power, some feedback circuits right here, the V out and the V sense. And this block right here is the 5-volt power supply for those drivers, and it's just a little switching converter, a little buck converter, the LM50185. Now built inside this chip, you can see that it also has a drive stage, much like the driver chips themselves. But having a drive chip versus having the drive built inside the chip, when you're trying to drive something that takes a little drive signal. Now remember, the GaNs, they like to be driven with 5 volts, which also makes them efficient because they're not driving the capacitors as high. That's pretty interesting, huh? These LLC converters are pretty complex. Isolation, switching fast, tons of power, all in a very small package. But the brain power is that microchip. It's controlling everything. And it's pretty sophisticated. The controller, it's a 16-bit digital signal controller. I mean, again, microchips pushing the future too, because a lot of the really complex circuits that are going to, actually the package size is driving that, and the power and those high frequencies. When you're doing all those things together, you need something like that, something that has super fast ADCs in them with, I think, 12-bit resolution they have, a bunch of op amps, a bunch of comparators, and the PWM circuit all combined in one microchip, a PIC. You guys may have heard about PICs, maybe used them in the past. There's all kinds of different PICs. I've used them in, I haven't done anything anywhere near this. Hey, this is the future. But I've done some power supplies. Actually, okay, maybe I should brag a little bit. I actually did build a little small card. It wasn't much bigger than this, with a microchip on it controlling, I think it was a SEPIC converter. Yes, it was. And I actually had it's kind of interesting. I actually had a sine wave on the output that was controlled by a sine wave on the input. And that went up into the German portion of the International Space Station. So, yeah, kind of proud of that. I don't know I haven't really told too many people about that, but yeah, I think that's pretty cool. But this guy here just blows my mind. I mean, this is nuts. Yeah, so let's go look at that microchip, okay? Just to show you this microchip part, this is just such a cool part. This, look at the specs on this thing. 32-bit multiply support. I mean, 6-cycle divide. It's just got a lot of hardcore math in here, I think. Look at this thing. It has a 16-bit DSP RISC CPU. I mean, this stuff looks just crazy. High-speed PWM, 4 PWM pairs. You can see the specs right through here. The A-to-D converter, it's a 12-bit resolution. I mean, this is pretty darn powerful. Small pin count from 28 to 48 pins, depending on which one you choose from the family. 64 kbytes of flash memory. I mean, you can see for yourself all the stuff this thing has in it. This is just pretty darn cool. In the past, when I've used intelligence on my power supplies, I've used microchip just because I just think they work great. For me, I mean, this thing's over my head, but for me, I've been able to at least work with the software guy and use these things and somewhat understand what the guy's doing with this. But yeah, just this one, wow, this just looks amazing. Okay, and here's the different parts of the family right here. Hey, by the way, that story I told you about, that power supply I did, I just want to give credit to the guy who wrote the firmware for the microchip. I put it in the board, put in the design, worked with a firmware designer, and actually contracted him to write the firmware. So yeah, that part, it's hard to find somebody that's good at firmware and good at power supplies, but I don't know what team did this, or if one guy did this. Oh geez, I'm gonna have to put his picture on my wall. Alright guys, hey, what do you think of that? Tell me if you're as impressed as I am. Obviously you can see how impressed I am. I want to thank EPC for sending this to me. That was super cool that they sent me an email and said, hey, we know you're interested in this stuff, you want to check it out. Yeah, so this card right here, and I think this card here, they both cost about the same, I believe, like around 380 bucks, something like that on DigiKey. They're expensive. They're meant for people to test them out to see what's possible, so they can not so much use this actual device, the artwork, which chances are they'd give you the artwork to do it if you wanted to, but they're just trying to show their GaNs, their FETs, you know, and they're just showing you what's possible. Okay, that's kind of what it's meant to be. It's not meant to be something that is priced. You know, you may look at that and go, "Wow, that's too expensive for that little converter." But somebody who builds converters, not FETs, they could probably build that package and put it together in such a way that they could make it, you know, a lot less expensive. And anyway, so that I just wanted to explain that because some people, when they saw the price of this, it kind of blew them away. EPC provides things like this to engineers like me, power engineers, who they hope will use their products and, you know, and my designs in the future, which I really want to. I mean, they're a leader in the field, obviously. That's proof right there. There's another item of proof. So, yeah. Oh, did you guys want to do a test? Alright. Take a little longer, but what the heck. I've got it all set up. Bring the camera over, show you what we're going to do. Use a little thermal camera. What we want to do, what I want to do anyway, I won't be able to take it up to full power. I don't think yeah, I probably could, but anyway, I'm going to do something convenient. I got a load right here. I think we can get it all in one camera shot and be able to see everything that's going on. And what I'm going to do is I'm going to take it up to 100 watts first. And let's just see how hot it gets without any airflow, okay? use a thermal camera. We'll look at the ripple with no load, with the load, and then we'll take it up higher, okay? But yeah, let's just start off that. And we'll do some load transients to see how it behaves, okay? Sure, it behaves really well, but now I'm not getting real critical with the little spring clip on my probe and doing all that kind of stuff. I just got the normal ground strap, so yeah, they might not be the best measurements we could take, but it'll give us a good idea. Let's do it. All right, let me quickly go over the setup. Here's the board, the input. The input power is coming in here. I also have this meter right here reading the input voltage. This guy is looking at this little thermal sensor right here, type K, and it's 22C right now. And this Hioki is looking at the output voltage. And the output, there's a sense and an out, so I have those strapped together on both plus and minus side, and then the load is right here. I just kind of set up this with this little load just so we can kind of see everything in the same picture, and that is coupled AC, so we're just looking at the ripple, okay? And it's 50 millivolts and 500 nanoseconds per division. All right, I'm going to go ahead and plug in power. Okay, you see I have 40 volts coming in, 22 degrees, and right now, I don't know if you can read the load, but it's not turned on yet, so let's get it up. Okay, it's set for 3 amps. I'm going to go ahead and just turn it on at 3 amps. There's the output ripple, by the way. That's zero load, okay? And that is with 3 amps. So we have 10 volts, so 30 watts. And let's just watch the temperature, see how fast it goes up. I'm going to try to keep this on, the thermocouple down. I'm going to crank up the current a little bit. 4 amps. There's 5 amps. So we have 50 watts out. Okay, there's 7 amps, 8, 9, 10 amps. Okay, we're at 10 amps, that's 100 watts. And I'm just curious, with no airflow, how cool this thing stays. Now, let's just say we're only at 95% efficient, which we're probably at 97. If we're at 95, we'd have 100 watts. We'd probably have about 5 watts dissipation in that module. Now, the ripple, that's 50 millivolts per division, so that's not bad at all. Again, I'm not, coupling, or I don't have my probe with the little spring clip on. It's just a ground strap, so you're going to pick up some noise that way. But yeah, not bad at all. 10 volts output. Okay, I haven't really seen the temperature change much. It's up 25.7. Now I've got this Hioki. It's a 50,000 count or 60,000 count meter. It's a 10 volts, and the AC, it goes up to 100 kilohertz, but at 100 kilohertz it doesn't see any ripple. It's just creeping up very slowly, right? I'm going to creep up the power a little bit because I thought we might see a little bit more temperature rise, but it's going so slow. Okay, there's 11 amps. Whoop, I think that's my power supply kicking off. Yeah, that was my power supply. I had to bring up the current limit. So it just was off for a few seconds there. Okay, we got 10 volts coming out. We're at 12 amps. 13 amps. Okay, there's 15 amps. So 150 watts. Still see a very slow temperature rise. Okay, I got this little thermal camera. Let's stick that in there. There's a little cursor that'll jump around and find the hottest spot. I think I'd say about 39 degrees in there. Okay, I'm going to go up a little higher. Let's keep an eye on this. Okay, I still see about, I can see about 40 degrees maybe. Okay, we're at 18 amps. I see about 41 degrees maybe. Yeah, about 41. Trying to keep that thermocouple down. Okay, what do we see? About 40, 41 and a half. 18 amps. I think that's pretty darn impressive. I'm going to let that thing run, and I'm going to change my scope to DC. You know what? I just realized I had that on my differential probe just before, and I had that at 50x. Let's go back to AC coupling and get a real picture of the ripple. Okay, there's 50 millivolts, there's 20 millivolts. Okay, this is probably going to look better then, right? There's 20 millivolts, 10 millivolts. Okay, I'll get the load back on there at 18 amps. There we go. Alright, so that's probably even more impressive, right? Sorry about that. I just noticed as I was changing that to DC. That was on 50x where my probe set at 10x. That's better. You can see the frequency down here, maybe 1 megahertz. Kind of bouncing around, 1.7 sometimes it sees. Okay, that's 18 amps again. Just check. I see 42.8 degrees. Okay, now I want to go DC. Alright, so I've got the load set at 15 amps. Let's go ahead and turn it on and see a step from 0 amps to 15. Okay, so it jumped up to about 10 and then slowly climbed. But even that jump right there, you saw a very small glitch there. Now this is 2 milliseconds per division, so yeah, it's not super fast, but yeah, the power supply didn't care about that at all. Let's capture a turn off now. Okay, I'll get the trigger to trigger on a falling edge, and let's try to capture that. Okay, well, it dropped off. You know, we're up here about 15 amp. It dropped all the way to 0 in this time frame right here, and we see just all it does is just go back up to where it was. So at least with this type of slower turn on turn off, the power supply doesn't care at all. Okay, just going back to the ripple real quick, 10 millivolts per division. Let's just freeze that and take a look at it, okay? Well, hold on a sec. That was 0 load. I'm going to go ahead and put 15 amps load. It doesn't look like it affects it very much at all, right? I'm going to freeze that. Okay, I just zoomed in on the waveform so you can take a close look at it. I'm going to go ahead and spread it out a little bit. 200 nanoseconds per division. So we got 2, 4, 6, 8, 1 microsecond. So that'd be 1 megahertz, right? So pretty cool. You know, it doesn't look bad at all. That's 10 millivolts per division on a 10 volt output. And that's with 15 amps. Talking up EPC, but why not? Man, the future's here, like I said. It seems like I keep repeating myself, so I'm going to close up, say thanks to my patrons, appreciate your support. You can become a patron for as little as $1 a month. And I want to thank everybody for watching the videos, supporting the channel. Thumbs up to the channel, to the video. That helps the YouTube analytics, helps the channel a lot. Free way to help support the channel, so appreciate it. And hey guys, we'll see you next time.